All right, we're in section 1.3 right now. We're talking about limits at infinity and infinite. I know that's a weird title, but what we're talking about are limits as x approaches infinity or negative infinity, as well as the types of limits that we've already seen where a limit goes to infinity or negative infinity. To start us off, so far when we have looked at limits in the previous two sections, our limits have always been of this form. The limit as x approaches c of f of x, where c is some finite real number. And what we're going to do now in this section is start looking at limits where that c is replaced by either an infinity or a negative infinity. And as we've already said before, the symbol infinity, or negative infinity for that matter, does not represent a real number. And so for that reason, you kind of have to think of these limits in different terms. We don't think of x as actually approaching some specific value, but instead, when we see the limit as x approaches infinity, we're really thinking of what happens to our function f of x as x gets arbitrarily large. As I continue plugging in larger and larger and larger positive numbers, like x equals 1,000,000, x equals 1,000,000,000, equals a trillion, larger and larger positive numbers without really slowing down or stopping. Is the function f of x skyrocketing to infinity, negative infinity, or does it seem to be leveling out somewhere and approaching some finite value? We're going to see all of those cases occur here, but that's what this limit means. As x gets arbitrarily large, what does f of x appear to be doing? Similarly here, as x approaches negative infinity, we think of that as x getting arbitrarily small. And this gets a little bit confusing when I use the term small because there's two different ways of thinking of the word small. I can say small as in close to zero, in which case a number like 0.1 or 0.0001 or negative 0.0003 or something like that. Those would be thought of as small numbers in that sense, but I'm not talking about that sense. I'm talking about in the negative sense. So a small number in the negative sense would be like negative 1,000,000,000. Right? A number that's very far in the negative direction. That's what we're going to mean by small here. So this kind of limit is saying what is happening to the function f of x as x gets arbitrarily small in the negative sense. Is f of x going towards infinity? Is it going towards negative infinity? Is it leveling out and appearing to approach some finite number? So let's first look at an example involving a graph to try and figure out how to make sense of this. Here we have the graph of some function y equals f of x. I don't know algebraically what this function looks like, but we do have at least a graph to look at. Now here's the thing. If you're going to take a graphical approach to solving these limits, there is kind of a lot that you're taking on faith because remember, if I want to find the limit as x approaches infinity, then what I'm saying is that I'm letting x get arbitrarily large. I'm letting it go bigger and bigger and bigger, further and further to the right. And I'm saying, what is the function doing as I go out that direction? Well, I have a very small window of this function to look at. So when I look at what happens to as I go to the right of this picture, the curve appears to start leveling out right here. In fact, it appears to be approaching this horizontal line right here, which corresponds to 4 on my y-axis. We can count our way up. 1, 2, 3, 4. Okay. Now, do I know for sure if this graph actually is approaching 4 or if it's doing some kind of other thing as we go further out to the right? We don't know. But based on what we're able to see, at least this part of the graph seems to suggest that that function is approaching 4 as x goes further and further to the right. So we're going to assume that that is what's happening, just for the sake of this illustration. I would say that the limit as x goes to infinity of f of x is equal to 4. Okay? What about the other direction? As x goes towards negative infinity, what's happening? Well, again, I would go as far to the left as I'm able to see in this picture. And what I'm seeing is the curve kind of coming down and also appearing to level out here, which is a different line. This appears to be leveling out close to 2. My y value is 2 here. Now, again, do I know if this function is doing some other kind of different behavior on the part that I can't see? I have no way of knowing. So really, it's our best guess And in this case, I would just say, based on what I can see, the limit as x approaches negative infinity appears to be 2. Because that is what this appears to be approaching here. Now, because we have so little information that we can glean from just a small little snapshot of a graph, the graphical approach for evaluating these limits is not always super helpful. So we're going to spend more time working on other approaches. But I do have one more graph I want to look at before we do that. This is one that we have already seen before. And in fact, we've actually talked about the kind of behavior that this function has. This is the graph of the exponential function, y equals e to the x. The exponential function, from our first week of class, when we talked about exponential functions in more depth, we know that as you go to the left, the exponential function is approaching the x-axis. And as you go to the right, we have exponential growth. So this thing grows larger and larger at a faster and faster rate, and it never slows down. So what does that mean for this? Well, the limit as x approaches infinity of the exponential function e to the x is infinity. And remember, this is not a real number, but when we write this, when we write the limit of a function as x approaches something equals infinity, what we mean is that it gets arbitrarily large as x approaches this value. Or in this case, as x gets arbitrarily large, y is also getting arbitrarily large. That's what these two infinities together are telling us. What about the limit as x approaches negative infinity? Well, as x approaches negative infinity, that means we're going further to the left along our x-axis, and we see that our graph is approaching 0. Y is equal to 0 along the x-axis. So that would mean that the limit as x approaches negative infinity of e to the x is just 0. Okay? So, like I said, we're not going to spend as much time looking at graphs as we are kind of the algebraic representations of functions. But I do want to talk about a term that we're going to be using over and over throughout this section, and that's end behavior. So when we evaluate these limits at infinity, which is what we call it when we have a limit as x goes to infinity or negative infinity, what we're really doing is we're doing something called analyzing end behavior for a function. If you think of the word end, it means like the ends or I guess just the ends of something. Now these graphs, going back to this picture right here, don't necessarily have an end, but you can think of end as like the long-term behavior of a graph, what's happening in the long term. And that's what we mean when we talk about end behavior. More literally, if I ask you to analyze the end behavior of a function, I'm asking you to tell me what is the limit as x approaches infinity of that function, and the limit as x approaches negative infinity of that function, if it's even possible to say anything about those. So let's consider a polynomial, because what we're going to see here is that analyzing end behavior for certain classes of functions oftentimes boil down to a relatively simple technique. Polynomials have very predictable end behavior, and we're going to talk about how to determine that. But let's look at an example. F of x is equal to 2x cubed minus 6x squared minus x plus 5. I want to determine the limit as x approaches infinity of f of x for this function here. And I'm not going to use a graph. I'm going to take a numerical approach this time. So I want to plug in numbers that are approaching infinity. And literally what that means, because you can't actually approach infinity if it's not a number, but when we say approach infinity, what we mean is plug in larger and larger and larger positive numbers and watch what happens to f of x. Now, I'm not going to plug in a bunch of numbers. I'm just going to plug in 1 because that's enough to make the point that I'm going to try to make here. Let's plug in 1,000. I would consider that a large positive number that might reveal some interesting patterns here, okay? If I plug 1,000 into this polynomial, instead of just jumping to a calculator, I'm going to work this out by hand, and I'm going to make a note of something interesting that happens. So in blue here, I'm just putting the result of this first term of my polynomial after plugging 1,000 in for x. And then all of the red stuff that comes after it is just what I get from all of these remaining terms after plugging 1,000 in for x. And if you notice what happens, we plug in 1,000 everywhere an x appears. We do some some arithmetic, and I get down to this step right here where all of the red stuff is combined into this number, and the blue stuff is this number. Now look at the two numbers by comparison. In blue, I have 2 billion, okay? In the red stuff, I have 6,995,000. Now that might seem like a small number because, again, negative. This is a negative 6,995,000. We might think, oh, that's a really small number in the negative sense because it's in the negative millions. That feels like a lot. But this number is in the billions, which is like on the order of 1,000 times almost more than this. Not exactly, but it's 1 billion is 1,000 times more than a million. So this is considerably larger than this is small. And what that means is that this number in blue is going to dominate the number in red, and we get a significantly large positive number when we evaluate that difference right there. Okay, now that's a very large positive number, which to me says that the limit as x goes to infinity of this function is probably infinity. I have no reason to believe it's just going to level out at some really high positive number. It's probably going to continue getting bigger and bigger and bigger without stopping or slowing down. So this suggests, it doesn't prove, but it suggests to me that the limit as x goes to infinity of this function is infinity. But more important than just making that observation is that this first term just by itself completely dominated all of the remaining terms. Even though there were 3 of them, the highest degree term, which we call the leading term of a polynomial, contributed far more to the end result than any of the other terms did combined. And so what we're kind of getting out of this is the fact that the end behavior of a polynomial is completely determined by the end behavior of just the first term. Because in the long term, the remaining terms become essentially negligible. So that's really useful because that limits how much we have to pay attention to. So down here, after I kind of went through all that stuff, we can now think of the limit as x approaches infinity of this polynomial as just the limit as x approaches infinity of 2x cubed, just the first term or the leading term. So we already kind of figured from this example up here that this would be infinity. What about as x approaches negative infinity? What's happening to this leading term of 2x cubed here? Well, I could follow a similar method and just try plugging in a very small number in the negative sense, say negative 1,000. If I plug a negative 1,000 into this term, I get negative 2 billion. So very, very small number in the negative sense. This suggests to me that the limit as x goes to negative infinity, right here, of 2x cubed is probably negative infinity. It's probably going to keep getting smaller and smaller without slowing down or stopping. But I want to pay a little bit more attention to how this turned out to be negative in the first place. So if you go back to the original leading term that we were looking at, 2x cubed, there's really only 2 operations that are impacting the sign of that term. And when I say sign, I mean whether it's positive or negative. So the 2 things that impact that are the exponent that I raise that x to, and then the leading coefficient, which is the number I'm multiplying to it. That exponent, if it's from the leading term, meaning the highest, the term that has the highest exponent, we call that the degree of the entire polynomial. Whatever your largest exponent is, that's what we call the degree of that polynomial. I have that written right here. Okay, so 2 things impact the end behavior of a polynomial: the sign of the leading coefficient and the parity of the degree of your polynomial. The word parity in this sense means if it's even or odd. So I kind of describe what's going on right here, but basically, if you'll recall from like our work on exponents and stuff you've learned in algebra, if you take a negative number and you raise it to an odd exponent, then that number will come out negative. If you raise a negative number to an even exponent, that number will come out positive. So even exponents will turn things positive, whereas odd exponents will keep negative numbers negative. In either case, if you plug a large positive number into, or just any positive number into a term that's like x to a power, whether that power is even or odd, it'll still give you positive. So the only case where things can change is when you plug negative numbers in. But then on top of that, if you multiply any number by a positive number, in this case, like the positive 2 that I have here as my leading coefficient, then that won't change the sign. So if x cubed is a negative number, multiplying it by a positive will still keep it negative. But if I multiply something by a negative number, that changes the sign. So a negative number times a negative number now becomes a positive number. When we kind of group up all of that information, what it does is it gives me this table down here where I can now predict what the end behavior of a polynomial is going to be. So putting these things together here, I considered the degree of the polynomial and I considered the leading coefficient of the polynomial. So it's kind of looking at this table. If you have a polynomial of even degree with a positive leading coefficient, then that that polynomial will go to infinity as x goes to either positive or negative infinity. If you have an even degree but with a negative leading coefficient, then in both possible cases, whether x goes to infinity or negative infinity, your polynomial is going to negative infinity in both cases. If you have odd degree polynomials with a positive leading coefficient, this is the case that we had up here. Odd degree, so 3 was my degree, positive leading coefficient 2. In the case where x is approaching infinity, your polynomial will also approach infinity. And when x is approaching negative infinity, your polynomial approaches negative infinity. And then you get kind of the flip side of that if your leading coefficient is negative and your degree is odd. So what I would like to do is apply this. When you have this table, this might initially seem like a lot of memorizing, but you just want to think through it logically. You don't really need the table in front of you to solve problems like this. All right, so here in this example, I want to determine the end behavior of the following polynomials. And again, what that means is find the limit of each of these polynomials as x goes to infinity and negative infinity. So as we said before, doesn't matter how complicated this polynomial looks, all that matters is the highest degree term. As I look at my terms, I see that this 7 is the largest exponent that appears. So this is what I'm going to take as my leading term, okay? That negative needs to come with it. So that minus is a part of that leading term. Now what I'm going to do is look at the limit as x goes to infinity of my function f of x, which we said will be the same thing as the limit as x goes to infinity of just negative 5x to the 7th power. Okay? The entire polynomial, its end behavior is determined by just that one term. Now, I could go to that table and I could say, okay, I have an odd degree and I have a negative leading coefficient. What does that tell me? But thinking through it logically, if I'm plugging large positive numbers into this, it doesn't matter what the degree of the polynomial is. X to that power will be a large positive number. But then I'm going to take that large positive number and multiply it by a negative 5, which will turn that into a negative number. That suggests that this will become negative infinity. Notice also, I mentioned this right here, polynomials only ever have infinite end behavior. Polynomials will never have a limit as x goes to infinity or negative infinity that comes out to some finite number like 5 or something. It's always plus or minus infinity. So that's the answer for this one. Take the limit as x approaches negative infinity next of f of x. This is completely determined by that same term. So the limit as x approaches negative infinity of, I almost wrote f of x again. I wanted to write negative 5x to the 7th. Okay, again, I could go back to that table or I can kind of think through this logically. If I plug a very small, in the negative sense, number in here, then I'm raising a negative number to an odd power, which would stay negative. But then that negative number gets multiplied to a negative 5, and negative times negative is positive. This will give me a positive infinity. Okay, so by writing the results of these two limits, I have described or determined the end behavior for this function. And that's all we have to do. Okay. Next up, I have a more complicated looking expression. This is a polynomial, but it's not written in standard form. it's written as a product of two polynomials. Now I know that when you multiply two polynomials together, the result is always another polynomial. So if I want to find the limit as x goes to infinity of g of x, we're going to use the same result or the same technique as the last problem. I really just need to focus on what the highest degree term is. But I don't want to just look through the sets of parentheses and say, oh, 17x to the 10th, that's the highest degree term. Because really, I'm forgetting the fact that these things are supposed to be multiplied out. So I don't need to multiply everything out. I only need to do whatever multiplication would give me the highest degree term. And that's going to come from multiplying the highest degree term here with the highest degree term here, okay? So really all I need to do is figure out what is 5x cubed times 17x to the 10th. 5 times 17, that would be 85. X cubed times x to the 10th, we add exponents, that gives me x to the 13th. So I'm looking at the limit as x approaches infinity of 85x to the 13th. And I don't care what any of the other terms would look like because they won't matter for the limit. Okay, now as x goes to infinity, I'm plugging in a large positive numbers in for x, so it won't matter what the exponent is, that comes out positive, and then I'm multiplying it to a positive 85. Positive times positive is positive, so I get positive infinity. Limit as x goes to negative infinity of g of x. Same thing. The only part that matters is the limit as x goes to negative infinity of 85x to the 13th power. This time, x is a very small negative number, but a negative number to an odd power stays negative. Multiplying that to a positive number would keep that negative, so it becomes negative infinity in that case. Okay, and that takes care of the end behavior for those two examples. I'm going to end this video here. In the next one, we're going to look at a different class of functions.